Good morning, everyone. Welcome to this, the last day of our coding school. And my name is Ilya Sinayskiy, and I'm going to tell you a few words about introduction to machine learning. And it's going to be quite basic. We're going to look in the theoretical introduction to the very simple models, but with these models, we could do the analysis in principle of many other things. And what we're going to do afterwards, we're going to do several examples of application to predict some properties or do the prediction on some data sets in a real case kind of scenario for more realistic and some artificial data sets. And I'm going to mention some models which I'm not going to talk about now in the more hands-on part, but in that case we're just going to use with you some tools to see, can we figure out what's going on. Okay. So, and basically these slides is a kind of shorter version compilation or kind of partial compilation of some course on the machine learning, which was taught elsewhere in University of Pennsylvania. Okay, let's start. But with a very basic question: what is machine learning? And there are many definitions of what is machine learning, and the different researchers or different prominent researchers in the field have a different opinion. For example, there is opinion like this. So learning is any process by which a system improves performance from experience. Okay, so we have already a couple of keywords, so that machine learning is something kind of in which we have experience and the system is improving its performance in some way. There is one more opinion, which is saying machine learning gives a computer ability to learn without being explicitly programmed. And this is already very interesting and a little bit more precise statement. In which sense? Because what we're going to see, we're not going to program explicitly what we wanted to what should be the parameters, and the typical problems which you might study or you've been dealing with. You need to know, for example, if you want to solve, equation for something, you need to know the equation. And one of the difficulties of machine learning, or one of the difficulties of doing machine learning in general, is that that's a goal, that we want to program things not explicitly, and we want the algorithm to find the best possible parameters and best possible ways of doing something, or the doing given task. And there is one more opinion from a little bit more recent opinion, but it's also a little bit more about more specific type of machine learning, which I'm going to mention just now. It's algorithms that improve the performance at task with some experience, and you can formalize it mathematically by specifying what is the performance, what is the task, and what is the experience. And for example, if we're talking about something which is called supervised learning, or some other the types of machine learning which, or not supervised learning, reinforcement learning, sorry, yes, which is used for the training of the programs to play games. For example, or this one you can of course do also with supervised learning, but it wouldn't be as good as reinforcement learning. And for example, the task would be the playing checkers. The performance is the win rate, and experience is with the modern reinforcement scenarios, the computers are mainly training by playing with themselves. They even don't need humans for that anymore. Okay, but we're going to focus on much more simple examples. For example, we're going to focus on the task which is called regression, which is in this case, for example, we need to do a prediction. So we have the some index which is describing to you what is the size of the arc sheets on the planet in the certain areas. So the the ecologists measure that, they plot it against the years, and the question is that it's clearly we see that the amount of ice is decreasing, but the question is, can we predict how much ice on average is going to be in a certain time at the certain moment in future, and what can you say, and what is the best way of doing this prediction? Yeah, so the typical scheme for doing a prediction is looking like this. So we have some data, we get some algorithm, we train an algorithm, and training algorithm, and we're going to see a little bit more practically what does it mean. It means that we're going to have a model, and we can afterwards test this model, given it's a new data, and using our trained model, we can get some new output, and we could check whether this output good by comparing, I don't know, with experiments, with observation, or with some part of the data which we didn't use for the training. And we're going to discuss that just now. And sorry, I also do not see the slide because I'm in the full screen mode. If there is a questions, please, can you read them or indicate me? Okay, so now we're going to the 3 types of learning, which are kind of traditional. I mean, sometimes it's split, all the machine learning is split to the more types of learning, but typically and traditionally, or kind of as a zero-order approximation, you can say that there is 3 types of learning. There is a supervised learning, and supervised learning is that your input data is data kind of with the answers essentially. So you have, in this case, this is the example of supervised learning. Yes, so kind of we have a sizes of the average size of the ice coverage, and we have kind of year and average size of the ice coverage. So year is your input, and the output is average size of the ice coverage. Okay, so kind of input output, or you have the pictures of the cats and dogs, and the answer is cat or dog. Yes, kind of, and so you have both. And the model, what the model is doing, the model is trying to predict if you get a new picture of the cat or dog or human, it should be able to say, is it cat, dog, or human, and so on. Okay, so there is another interesting type of learning, which is called unsupervised learning. So, and this is, roughly speaking, the learning where you don't know the answers. So you only have an input data, and essentially what the algorithms are doing, they are allowing to look for some internal structure in your data, from which you could learn something new. And we're going to see what that means. And the last one, which I already mentioned with the checkers example, is reinforcement learning. And that is mainly used when you have some algorithm which is interacting, which could be interacting with a kind of external environment, which can do some operations, for example, do the moves on the checkerboard. And as a result of the moving of the opponent, the algorithm is learning what is the optimal strategy for the interaction with environment, and it's formulated with help of what is called policy to reach some desired task, which in the case of the checkers game or chess game would be kind of to increase the win rate. Okay, so again, yes, supervised learning in this simple case of where we have an input one-dimensional, output one-dimensional, so kind of it's not necessarily need to be the case. We have X and Y's, and what we need to find out, what is the best way, what is the best fitting way of of doing it, such that we're going to get the best prediction. Okay, so that's a regression task. Another very typical task in supervised learning is classification task. And what is classification? Classification is when you are given, again, some input data, and you're told that your possible outputs are, if here possible outputs are essentially any number as you see from 0 to 9, in this case, kind of the output is you can be in the class 1 or class 2 or class 3. You can have a multi-class classification. So if it's only 2 classes, so class 1 or class 2, it's only binary, it's a called binary classification. And for example, the typical task in this case is called, for example, is used in medical diagnosis, where you need to say whether the person with a kind of certain input data have a disease or don't have a disease. Okay. And what unsupervised learning is doing, kind of what is the typical graphical representation of unsupervised learning is we want to find some structure in the data, kind of, and for us with the human eye, we could really easily see that, out of these blobs of circles, we could really see that there is 3 clusters of the circles, yeah? And kind of, it's easy for us, and a lot of tasks which are still easy for human or relatively easy for human are still difficult for the machine. And so there are special algorithms which know how to put these kind of labels together, how to say that, okay, there is one blob of points, there is another blob of points, and there is another blob of points, and how to do it in a systematic way. And we're not going to talk about this particular thing in this lecture, but in the tutorial, we're going to have a tutorial where I will show you how to do this, what is called the k-means clustering, and also will give you a little indication how you can decide when there is enough clusters or not enough clusters. Because again, here we could easily see that, there is a 3 clusters, but in reality, we might have a situation when, first of all, it's very difficult to visualize data in 2D, or when you visualize it in 2D or in 3D, you could not see the structure because the data is so multidimensional. Okay, so, and where this clustering is used is in everywhere essentially, and it's kind of starting from the analysis of the network structures in the networks. So can you find, some influencers which are not that obvious in the Facebook, for example, and so on? Yes, can you identify the types of exoplanets, or kind of how can you visualize data which you haven't classified, and can you kind of, this is kind of unsupervised learning is very actively used, and we're going to touch a couple of examples of how it's used, or kind of how to implement it in Python. Okay, and the last one is reinforcement learning. So we need to learn how to perform a task from interaction with the environment. Yes, an example is the famous chess playing program, yes, and the famous AlphaGo, which was, I think, already mentioned today, some time ago. So kind of the AlphaGo playing programs, they were trained using the reinforcement learning, and the kind of naive picture of how it's happening. You have an agent or program which is interacting with environment, which means whatever the environment is, and afterwards it's based on the feedback from the environment, it's adjusts its action. Okay, so and machine learning is everywhere. We all know that. So we have a spam detection systems which are based on machine learning algorithms. We have some, or trying to have some self-driving cars with various degree of success. Yes, we have a recommender systems in the Netflix and in all the rest. So we have some little AI systems which are building into this smart homes, and kind of smart systems like Amazon's one, or Siri in the iPhones, and so on and so forth. And of course, besides that, fun applications have much more serious and interesting application. For example, in certain parts of the human endeavor where you need a specialist, it's already shown that the subset of machine learning, which is called deep learning, is outperforming, for example, on the tasks of the understanding some structures in the human brain better than the professional radiologist, for example. And this is already kind of established, and that's why kind of like certain forms of occupation will need to be rethinking what they're doing, or learn how to use these tools, because this is coming, this is happening, and machines in this certain class of tasks which are related to computer visions are definitely much better than humans by now already. Okay, it's also, machine learning is also used in scientific discovery, and one of the highlights, for example, is very famous AlphaFold from the same DeepMind, which is essentially solved, or kind of the demonstration good enough approximation about for the problem of the structure of the protein, which is a very famous problem, or kind of well-known problem, that kind of like, if I will give you the string of the molecules which is composed, or atoms which are inside of the protein, and I can give you even an order, it's very difficult to predict the geometric shape of this structure, and there were kind of many attempts to doing it, and the only attempts which give a really good answer was using machine learning, and kind of this was done by the famous AlphaFold algorithm, and you can later watch the, if you don't know about that, you can read the corresponding blog post. Okay, and also it's used, to enhance some astrophysical data in many other places. It's also used, for example, in my professional domain, which is related to the quantum computing and quantum communications. Okay, so there are some other very interesting applications. Yes, and now you can already see that the reference is a little bit outdated. First, machine learning is used to generate images, and now it's getting very good at it, because there is a whole website which you can try, which is called "This Person Does Not Exist," because all these faces are generated using something which is called generative adversarial networks, or it's the special machine learning algorithms, which, after being trained on a lot of images of the human faces, could start training you, generate new human faces which never existed. Or you can do the same thing with text, and in this case, this is example GPT-2, but you already probably heard that there is even better version which is available and which is extremely efficient, is something just called GPT-3, and corresponding the chat representation of it. ChatGPT. Okay, and okay, so now let's go into a little bit more into the details. So we have data, we have machine learning algorithms. Yes, we need to build a model which could now on the new input predict to us output. Okay, so now the question is how to choose machine learning algorithms. Which machine learning algorithms are there? Which models are available? And essentially, in order to do it, and what I'm going to focus on the simplest possible model, and we're going to start with the linear functions. And don't think that, oh, linear function cannot do anything. So in principle, they can do quite a few things, and the even better thing about them that you can analyze a lot of stuff using the linear models, and you can interpret them. This is another moment which kind of we're not going to discuss it today because we're not going to talk about no neural networks at all. But one of the problems with the neural networks is that, you know, they can be trained and they can be extremely efficient in doing whatever you ask them to do, but you have no idea why. And, you know, in the moment when you want to apply it in real life, you really would like to know why the network or why your algorithm have taken this or that decision, especially if it's kind of, you know, if the human life is at stake. Okay, so and with this type of models, which are going to talk today, and we're going to play in the tutorial, we do not have a problem of interpretability. It's there. You know, we can extract all the parameters, and we could relatively straightforwardly interpret them. Okay, so the simplest model, as I mentioned, is just a linear function, and everybody who have done a little bit of data analysis or a little bit of kind of elementary fitting have done linear functions. Yes, so in kind of in the simplest version, how it looks like. So we have input data, so kind of it's a vector of d entries, yeah, and it's kind of multiplied by the transpose vector of the parameters which we'll need to identify. Yes, x is called input, so also it's called features or covariances. So it's input data. For example, if it's, I don't know, some medical data set, it could be, you know, kind of the height of the person, weight of the person, afterwards, you know, some other characteristics, what is your typical pressure or current pressure, whatever. Okay, so betas are parameters and y is called label. So that's what's kind of spitting out. So for every set of x's and for the given set of betas, we can get some y out. Yeah. Okay, formally speaking, it could be formalized, kind of a little bit more formally speaking, it could be written like this. So we have an input data set, x1, y1, xn, yn, and x in here is a d-dimensional vector. So it's kind of, it's a list with d entries. Yeah. And the output is y, and y is just a number. In this case, a real number. And we could construct a linear function. And the idea is to choose betas in such a way so that y's are approximately equal to betas. And now we're going to discuss a little bit what that means and why we cannot always do it exactly, and why very often you don't want to do it exactly, because if you do it exactly, you might run into some problems which might be a little bit counterintuitive, but we're going to talk about them just now. So, okay, so typical notations which are going to be used for the lecture is I is index the examples. So we have here D numbers, and here we have one number of answer. And J will be indexing the entries of the each input vector. Okay, so and the goal is estimate beta. Oops. What does it mean? Estimate beta. You know, in this case, we're dealing one kind of each x in our examples with the I sheet is one-dimensional. So y is also one-dimensional. And so the idea is like beta will be just one number, but this number should be such that, or in this, okay, we're also going to talk about a little bit about the intercept term. So in fact, there will be two numbers in this problem. But the question is, we need to draw a single line such that we can make this statement that roughly speaking, all yi's could be described by this linear relation. And the question is, what does it mean? How can we measure it? And how can we formalize it? Okay, so, and this is a very simple example. Yes, so kind of, and again, the beauty of, you know, doing it with linear function or with the simple examples that we can visualize it, and afterwards we can take it from there. Okay, so for example, we have our blue dots. This is our data, is our axis, and we need to draw a straight line which describes the best of them. So what does it mean? It means that in order to estimate the quality of our fit, we need to estimate the distances, yeah, Yes, but if we just estimating the sums of the distances, some distances could be positive, some could be negative. So it's much better to take a squared. And so there is one more reason why you want to take a squared, because in fact, we are going to take a derivatives. And if you want to take a derivative of the quadratic function, it's much better behaved than the derivative, for example, of the absolute value. Because the derivative of absolute value have a problem in zero, while the quadratic function is good behaved. And there are some some other reasons which are related to optimization. Okay, so and if we just calculate things like this, so for every input, we calculate what is the prediction and subtract it from the output and take a squared, and we sum all of them and divide it by n. So we find the average like this, and this is called mean squared error. So we could suddenly kind of get some measure which could tell us in principle what is the loss function, or what is how good are we describing input data. Okay, so we have input and we need to find beta such, or vector beta that minimizes this thing. Okay, so on the fancy language in the machine learning textbooks, if you're going to read a machine learning textbook, you can have this notation, which just means is that we need to find, so kind of what is the solution for the input data set x, y, x, y. So we need to find such a set of betas, so such set of numbers, beta 1, beta 2, beta d, such that the loss function is minimal out of all possible betas. And although it looks a little bit scary, you know, in Python, it's very nicely implemented, so we can just go and see how it's done in Python. And just a little bit to you, an intuition behind what does it mean, kind of why, kind of what are we getting and why we want the quadratic function here. So let's put a very naive example. So we just put 3 points along the straight line. So very easy we can describe. We can calculate the loss function, and loss function will be 0 because we have a perfect answer. Yeah. So, but let's choose other beta, which going like this. And in this case, we just need to sum up this size, and the beta is a little bit smaller. So we get a loss function here. Now, if we choose beta like this, we get a loss function here. And you see, kind of, you can already get a little picture that, okay, so what you want to go down in the landscape of the values of the loss function. And that's exactly what you will do. So if you try, you know, betas which are going to be on this side, I don't know, can you see my mouse pointer?
Yes.
Okay, yes, good. Okay, so, and that gives a little intuition that, you know, and in this very simple one-dimensional input, one-dimensional output, it's very clear that, okay, we will walk along the parabola. In general case, so for example, in two-dimensional case, we can get a little convex bowl-shaped thing, or if we just look from the top and just look on the kind of the equipotential lines, we're going to get an images like this. But, you know, kind of when your data is d-dimensional, so kind of when you input a lot of points about whoever, kind of, or kind of whatever is your input, you get like this multi-dimensional ball in which you need to walk down the kind of the down to the local optima, but or to the global minima. But we're also going to see why it might be not the best idea. Okay, but this is not the only loss functions. So there is also mean absolute error, and it's used the absolute value. And as I mentioned to you, so you can use this one, but in the moment when you implement it numerically, what you need to do, you need to take care of the behavior of small kind of change of your function around 0, because the absolute value is non-differentiable in 0. So, or mean relative error, yes, or it's much more commonly used is kind of the R2 score, and R2 score is mean squared error divided by variance. So the higher the better, and the best possible the best possible R2 score is 1. Okay, so now going back to our linear regression. So now what do we learn? And that will be kind of like, you can replace word linear regression by any other regression model. You know, kind of like it could be support vector machine, it could be, I don't know, some decision tree or forest or random forest regression, it could be neural network. But essentially the idea is that you have a model family, you have your loss function, And your job is to find the best parameters of the model by minimizing the loss function. Okay, and now there is an interesting idea how we can make what sounds linear work better. And this is called feature engineering or kernel trick, or there are many names which mean the same. Let's say that our data is quadratic function. Yeah, again, our artificial data, and it's behave like this. So if we try to fit in linear function, we're not going to get a good result. Yeah, but what we can try to do, or we can try to do another linear function, but it's still bad. But what we can do with the input data, so we can say that the same thing, instead of multiplying this beta by the vector of input data, we're going to multiply beta by the vector of transformed input data. And this is called feature map, or it's called kernel trick, or it's just a transformed input data. And partially you've done that, because I've seen in your last week course, when you were dealing with a little bit of that data analysis and pandas, you were trying to fit I think something like sine or cos function with some polynomial of the different degree. So this is absolutely similar, but the idea is like, you know, that this feature map could be, it's not necessarily polynomial, it could be something else. Okay, and for this particular example, we can consider feature map like this. So it's take every point and just also added x squared, and in this case, the model family becomes something like this. Yes, kind of, it's still kind of our, from this point of view, our linear model, but with the feature map like this. Okay, and in that case, of course, we can perfectly fit it, because that is clear. But this is just to give you an idea that, you know, linear function doesn't imply that it's linear, like, you know, linear in input. It could be linear in some feature map or kind of in some kernel. Okay, so, and the kind of the design appropriate feature maps is kind of a whole skill by itself, and there are, you know, certain books which are written about kind of learning with kernels and some other books like that. Okay, so, and yes, you can have a polynomial feature maps. Yes, so you can have, I mean, quadratic features are common. Yes, also what I mentioned to you, very often people add the intercept term to your linear function. Yes, you need to use it, because yes, again, for the same example of the ice sheets, without intercept term, our curve will go, kind of our straight line will go in absolutely different direction. So, and or kind of, yes, some other encoding of what is called non-real inputs, or kind of some evaluative statements. Okay, so now we have, so the algorithm also with nonlinear features reduces to linear regression, because we just need to calculate for the every input data, we need to calculate feature, and now we apply linear regression not to the input data but to the feature map entries. Okay, but now the question is, now we're coming to the question, do we really want to perfectly fit the data? And this is also a very non-trivial question with a very kind of simple answer that no, but we're now going to see why. Because, you know, if we get the points like this, you know, we can take some polynomial feature of some high degree and the polynomial will perfectly fit it. But why it is bad? Because when we get the new points, which we didn't know when we were training, these points might be far away. And from this point of view, you know, fitting this curve just with a straight line is a much better solution. Yeah. So kind of, because the distance from this curve to the new inputs is very large. And this is kind of a serious problem, because this is called the problem of generalization. And in fact, what are you looking for in machine learning? You are looking for into the building a model which will work good on the data which you haven't seen. Because to make a model which will work perfectly on the data which you have is a very simple task. There is more than enough algorithms which can do. But the task is really that you need to be able to predict good enough something which you haven't seen. And this is kind of the very serious direction. And there are tools and tricks in machine learning how to do it. Okay. So how you can try to approximate that generalization? So what you do, if you get your input data, you know, set of years, size of the ice sheet. So in order to fit the model and to know how good it will generalize, what you need to do, in fact, what you want Okay, yes. Okay, so in fact, what you want to do, you want to split your data into the test and training. And you train only on the one subset of data. And afterwards, you pretend that you didn't have a test data, but you use it for testing and to see how the good model is performing. And we're going now to see how it's, and kind of in the examples, we're going to see how it's done. And now it's done, of course, automatically. So kind of like you just need to call a corresponding function, which is called test training split, which is a part of standard part of the scikit package. And we're going to see, you know, how it works. Okay, so, but before we're going to discuss that, we need to discuss two aspects which are called overfitting and underfitting. So overfitting is when you take your training data and you could describe it perfectly, but the new test data is described very poorly. So this is called overfitting. And underfitting is when your training data is described poorly, but also a new but also new points will also be described poorly. So it means that, you know, kind of in this case, we see that, you know, the model is have too many kind of, it's called have a too large capacity so that we cannot train it properly, and the simple linear model will work here better. While here in this underfitting scenario, just a quadratic model will be good enough, and the linear model is just too poor. I mean, it doesn't have, and formally speaking, its capacity of this model is not sufficient to describe the input data, and we have an underfitting scenario. And what you want, ideally, you want to be somewhere in between. You don't want to underfit, but you also don't want to overfit. You want to be in the just right area. Okay, and how it's done, that's what you're trying to do, yes. How you try to detect overfitting vs underfitting. So you have your data, you split it into the training and test, and you do the training on the training, and afterwards on the test data, you do only test to understand how good is your training, or how good is your training happening. Okay, so what is now our strategy would be, we have a input data, we split into the train and test. Afterwards, we do our algorithm, our linear regression, we get beta, and we're evaluating the training loss, and we're evaluating the test loss. And in principle, you want these two numbers to be comparable. Of course, the test loss is usually a little bit higher than the training loss, but you know, if your train loss is 0 and the test loss is, I don't know, huge, it means that you are doing something wrong. Okay, so training loss is small in this case in overfitting, test loss is large. Underfitting, training loss is large, and the test loss is large. So they're both large. And so it means that in this case, you need to increase the complexity of the model. And in this case, it means that you need to decrease the complexity of the model. And on the point of view of the polynomials, it means that here you just need to increase the power of polynomial, and here you need to reduce it. Okay, yes, so how to fix? Choose the right model. How we can choose the right model? We need the kind of what I mentioned to you, kind of in this case of simple polynomial fitting into the data. We just need to choose the right power, and kind of, but for more general models, there is a characteristic which is called capacity. So the capacity is kind of an ability of the model to capture adequately the given data. Okay, high capacity, you have more likely to overfit, and it's called that the family have a high variance. And the low capacity is more likely to underfit, and it says that the model have a high bias. And the linear regression capacity corresponds to the feature dimension, so the number of features, or to the kind of power of your polynomial. But it's not necessarily polynomial features. You can, that's why kind of this power correspond to the feature dimension. So overfitting or high variance, because you can very often hear Prof, the word. Yeah.
There are a couple of questions on Slack.
Okay, let me check. Yes, you can interchangeably use the term model, and okay, the algorithm is the process how we train the model. Kind of the algorithm is everything. It's not really interchangeably, but because the algorithm is kind of algorithm of doing something, and model is just a model, is just some form of relationship. Okay, can we have MSE equal to variance? Under what circumstances such can happen, and how such situation will affect your model. Okay, so can we have mean squared error equal to variance? Okay, so let's think about that. So let's go back to the definition of the mean squared error. So where is our mean squared error? Yeah, so this is our, okay, this is our loss function. Okay, this is our mean squared error. And to the variance, but isn't it, so variance of what? So just go back to the, sorry, okay. Can you specify variance of what do you mean? Otto von Bismarck. That when the variance equal to MSC, we have R2 of 2. No, when the variance is equal to MSC, we have R2 of 0. Sorry. No, when the variance is, when they equal, R2 is 0. Which is not perfect. Okay, can you explain the difference between overfitting and underfitting again? Okay, so let's go to this image. So overfitting is when you train your model in such a way so that it's very good in describing your test data. So you're training, I'm just telling you, oh, you need to minimize your test loss. So you need to describe your blue dots. Yes, so this is your training data. So you try a linear function, it's not good enough. You try quadratic, cubic, fourth order function, and suddenly you find some function which give you loss of 0, for example. And in this picture, the loss is 0 on the blue data. Yeah. But suddenly when I give you the new test data to try, you see that the loss is huge, which means that you overfit. Okay, so it means that you overtrain on the training data, and the kind of on the test data, your performance is very bad. So it means that sometimes it's happened that you can have a very small loss, extremely small loss, but it's also work good on the new data. Maybe it means that your new data is very simple. If all your data is lying along the straight line, and if you take away half of the points, and you can still predict the straight line because you need only 2 points to predict the straight line. Yes. So in that case, adding new adding new training data, or kind of adding new inputs will not change your the performance of your model. But in the moment when you if your loss on the training data is very small, but the loss on the new data is huge, it's large, it's mean that you overfit. So it's mean that your model is too good in explaining the known data and extremely bad in explaining the unknown data. So what is underfitting? Underfitting, it means that you are bad everywhere. So you're bad in explaining your test or your training data. So you just take model which is too simple to explain your data. So for example, as in this example, so your data is more or less quadratic function, or in this case, it's a quadratic function, but you want to fit quadratic function with a linear function, which you cannot adequately. Yes, so it means that it will be bad while you train, the loss function will be large, but also loss function will be large when you add new points from the quadratic function, kind of like, of course, if your points will come from here, the loss function will be okay, but if your new points will come from here, your loss function will be large. Yes, and kind of the fact that your points might come from here or not from here, it has something else to do. What you wanted to make sure that your test and training data are coming from the same distribution, so they have roughly they roughly cover the same area of possibilities, so that kind of you don't end up just randomly taking new points from here, because linear function will work very good here, but here it will work very poorly, while this function probably won't work anyway good except in the small neighborhoods of these points. Okay. Is there data preparation before machine learning analysis? Yes, of course. And we're going to see it in the tutorial, but I'm not spending any time on data preparation, because many things about the data preparation you have in your pandas part. Because in the pandas part, what you were shown, how to calculate some basic characteristics of your data set and how to do some basic plotting, but in the we're going to see, yes, how you can do it. Yes, yeah, it could be equal to, yes, that would be 0. Yes. What is the best way to minimize loss function? That is, we're coming to the best ways to minimize the loss functions. Okay, so let's continue. So when do we stop? So we need to choose the family correctly. Okay. Okay, so that's a graph, or kind of like, that's what you want to do. That's your typical loss function, depend as a function of the capacity, or on this axis you might have, for example, of the order of the polynomial which you're fitting in. Your training loss, usually in every decent algorithm, when you increase the complexity large enough, will go down. Especially, it's very nicely is seen, for example, with the neural networks, because you take bigger neural network and your training loss is going down. But what is happening to the test loss, what you see, that your test loss usually is also going down, but not necessary. But if you do things right, it's going down to some point, and afterwards it's begin to go up again. And what you wanted to do, essentially, where do you want to kind of to stop? You want to stop somewhere when they're both going down and the test loss is not yet going up too fast, because it means that you are kind of, you have chosen the right degree of this polynomial, for example, in this example. So as an exercise, for example, what some of you can try. So just generate, for example, the bunch of points with a little bit of noise with the, I don't know, cubic function. Yeah. And try to fit it in with the features, with a linear, quadratic, cubic, fourth order, fifth order, sixth order, for example, and just to see kind of and calculate the loss function. And if you do things right, what you will see that definitively, your loss on the test data will decrease, and afterwards at some stage it begin to rise again. And it means that you need to choose the parameters of your system, or your capacity of the model in this case, somewhere here. Okay, so there is one more important thing which we are going to play with, and this is called regularization. And why regularization is important. Let me see. Okay, let's put it into this graph. Okay, so so sometimes what is happening that when you train your model, some parameters in your model, some betas might suddenly become large by some random scenario, and you might be kind of following something which is called some local minima. So you can just get stuck into them, into that subsets, and all the rest betas are not trained and not changing. And because it could be a function of your algorithm, it could be, there will be several reasons for that. And the question is how to get out of that, because, you know, the nice picture which I've drawn to you of the convex search space or kind of optimization space is far always not the true. It's true only for the linear function, but in most other cases, you know, the search space is much more hilly, and you can get some in the local minima. And the question is how you can force the algorithm during the training to look to the more possibilities. And what you can do, you can add a special penalty. You add in by design, you add in a penalty for the values of betas. And so from here, you see that, you know, if you have some betas which are very large, they're going to give a big contribution to this penalty, and they're going to have a kind of very large loss function. Yes, so, and in this case, what you want to do, you want to try to have more preferred case would be to have more betas, but there will be smaller values. Okay, and lambda in this case is called a hyperparameter, which means, okay, that is an extra parameter which you need to train and choose for. So it means that you need to choose lambda, afterwards train for beta, afterwards choose another lambda, and afterwards train for beta, and see kind of how you go in the space of optimizing lambda. Kind of graphically, it corresponds to the following picture. So this is our ball of minimizing loss function, but we have an extra ball which is created now by this this regularization parameter. And essentially what you want to do, so kind of if you are here if your regularization parameter lambda is too large, you will fall here. If your regularization parameter is 0, you fall here. But in fact, you want to be somewhere in between, because it will minimize the full loss. And again, why you want to do it? Because if you have a better representation of the beta in the space of parameters, you have a better chance for generalization, so that you can do better work on predicting the numbers which you don't see. Okay, so there is a question about how to handle the missing data in the time series. Okay, I'm not going to talk at all about how to handle missing data, because all the data sets which I'm dealing with, they have they will be with the full data. But the idea is that there are special methods how you can handle the missing data, and there are several strategies, and it depends on the properties of your time series and essentially what you can do. So there are some very simple and naive strategies. So, you know, you can, if you have a missing date, you can increase, or you can just plug in the previous date or next date, or you can plug in average if they're far away between each other. And there are some other strategies how you can do it. The same thing in reverse is to the values. So you could kind of, if you have a kind of day 1, day 2, day 3, day 4, day 5, and you have missing values of the, I don't know, day 3, you can substitute with an average, or you can sometimes you can substitute with something else. It depends. I mean, it's a special kind of topic of itself, how to deal with the missing data, and it also depends what kind of data or time series it is. So it's there are methods, there are many methods, and kind of, and unfortunately, I'm not going to talk about that. Okay. So, and there was one more question. What do you mean noise? What do I mean noise? It's mean when I ask to do the fitting exercise, noise, I mean exactly, it's just a random number. So because, you know, I show you example of the data which, you know, which is perfectly following given curves, but in reality, it's never the case. Yes, because if it's, I don't know, if for example we're talking about the data of the measuring of the height of the people, yes, or measuring the weight of the people, there is no perfect measurement. You cannot measure them perfectly without mistake the height of the person or the weight of the person, or kind of your device which is measuring, I don't know, the sun radiation could not measure it perfectly. So in order to simulate something, in order to simulate more realistic data, what people usually do with the synthetic data sets, they have some major function, for example, like the x-square, and they can add some random Gaussian noise, for example. But in the real data, there is always noise. Okay, sorry, no. Oops, where am I going? Okay, so we were here. Yep. No, there is also a question, are there various four functions, methods of regularization, or it's only to the norm of beta? No, it's not only norm of beta, because this is called L2 regularization, and as one can guess, there is L1 regularization. And for this particular model, for linear model, there is only two major regularizations. It's L1 and L2 regularization. And they serve similar functions. And in scikit-learn, the implementation which can do both, I think it's called elastic net. This will be just a linear model with the both type of regularization, and it could optimize them both. Okay. So now the question is, because I told you that, okay, now we want to introduce some regularization, which is called penalty, yes. So because we don't want perfect solution on the training data, we want good enough solution everywhere. So now the question is how to choose this lambda. And in order to choose this lambda, what people do, they are doing more splits of the data. And that, of course, have its problem that you have your training data, you have your validation data. So you use training and validation to train your betas. And afterwards, you use test data, for example, to test for the lambda, so vice versa. Okay, so given Z, we need to split it to the three pieces. So run regression on Z. Okay, and yes, okay, we're running regression on Z to obtain for given lambda of t to obtain beta, and afterwards evaluate loss. Yes, and afterwards we're trying to choose best lambda of t. Yes, which have a lowest validation loss to obtain again betas and so on. And what you can do in order to do things even better, and this is called cross-validation, and we're going to do it. So you're splitting your training and kind of validation, or training and validation data into the different subgroups. Kind of like you take, okay, all these data will be training and then validation, and afterwards we're going to see what is the performance of the algorithm. Afterwards, we're going to take as a validation medium data and train it from the beginning, and again, but the test data we don't touch. And afterwards, we're going to check the performance between these two algorithms. Because why you wanted to do it? Because you want to know that your algorithm, or kind of your model, is trained. Your model is trained by the algorithm, is trained well enough on the whole given data, and its performance is independent of your splits. So essentially, that's giving you better ideas that the good performance which you see is related to the way how you train algorithm, and to the how you train the model and the weights you obtain, and not to some random fluctuations in your data distribution, because you can be given data which is ordered in some way, and this way is irrelevant for the model, and in that case you need to reshuffle it in some way. But doing the procedures like this help you to do things, and usually people do 5-fold or more-fold cross-validation. How do I choose between L1 and L2? You do both, and you see which works. Does validation set come into play only in the context of the cross-validation? Not necessary. You can introduce it on earlier stage, but I mean, in the cross-validation, it's the most natural thing to be, because it's like you take this split of training and validation as your main kind of the training facility, so to say. You train your data and you check how your data is performed on validation data, and you use it to update the parameters of the model, and you never touch the test. Yes, you do this cycle with the different portions of validation, you get a different set of parameters, and afterwards you see how you perform on the test data, which you never touched. And in that case, it gives you a hope that, on the data which you have never seen, the model will perform at least comparably to the performance on the test data. Oops. Okay, I think I stopped sharing. Okay. Okay, so we were here. Yes, in general, you deal with the k-fold cross validation, but also keep in mind that if you give not too much data, all that becomes difficult. If you have 1 million points, okay, you can slice and dice them in many possible ways, but if your data set is 100 points, it's getting a little bit difficult. Okay. So yes, kind of like in principle, you want to have as many splits as you can. And but again, this leads you to another trade-off, which is compute vs accuracy. So because the idea is like you split into the 3 pieces and you do 3 times, so it means that you execute your training algorithm 3 times longer. Usually people do like 5-fold or 10-fold cross validation, so it's kind of like algorithm which is trained for 1 unit of time, now is training 5 or 10 times longer. And that's what you need to keep in mind, But this is always kind of the ratio between how much compute you have, so how much computing power you have, how long are you prepared to wait before you can start using your model. Okay, so let's go quickly through this, because with linear regression, the beauty of it and why it's very popular in theoretical computer science, that you can solve it analytically. And it means that a lot of these concepts which I mentioned to you, which are related to the overfitting, underfitting, or estimation and error, or formulation, or kind of dividing the error of generalization, so kind of finding the ideal model, kind of for the way to the ideal model, you can do analytically, and you can do analytical estimates. And that's why it plays an important role from the theoretical understanding. But the beauty of it that if you understand this, the crucial concept, the loss function, the cross validation, and regularization, when you go to the more complicated model, which you already cannot treat analytically, you at least have a very good intuition what all those words means. Okay, so yes, we can rewrite linear model in the vector form, obviously. Yes, we can also vectorize the loss function, which is very interesting. So we can rewrite the loss function also in the vector form. It will look like this. And now we can analytically calculate what will be the point of the minimum. So for that, we need to take a gradient with respect. So we need to take a derivative in all directions with respect to our training parameters. And it should be equal to 0 here. And if we do a little bit of math, we will get something like this. And putting it to 0, we'll have an equation like this. And now the only thing which we need to do, we just need to invert this matrix. Yes, and formally we can write it. And again, we can do it under the assumption that the matrix is invertible. But because this matrix is not necessarily invertible, or the process of the matrix inversion could be very kind of non-unique if the matrix is large enough and have kind of problems with the eigenvalues, that this operation is not always so well defined. But in principle, you can do it, and there is a nice example of non-invertibility. So if our matrix of input data is looking like this matrix is not invertible, but this is clearly why, because what you will get that for every given beta 1, there will be always well-defined beta 2, which are dependent variables. Okay, so there are many other kind of issues with the kind of analytical solution, and that's why usually it's never done. But again, it allows you to analyze all the things very nicely, and that's why kind of it exists. Yes, so kind of like So there is a complexity associated with the inverting of the matrix. And for example, for the large enough data, 10 to the 4 features, it would take kind of quite a long time. And also sometimes what you have with this, such objects, they can be what is called ill conditioning or barely invertible. So it's mean that, you know, it's not your 2x2 matrix, which you can do with your pen and paper. It could be a huge matrix, which would be long, and the inversion might even not work. Okay, so, and the best strategy and the next strategy, which is, okay. With a cross, there is a question with the k-fold cross-validation, how you determine k value is suited for the certain case. In principle, you want the k value equal to the number of data points in your training, in your kind of the training, and yes, kind of in your training set, so that the validation is only 1 point. But in that case, you will need to execute your algorithm as many times as data points. So you just usually the kind of the rule of thumb is between 5 and 10 fold cross validation is good enough. Does the number of folds depends on the data size? Yes, you know, if you have enough data, you know, 10-fold cross validation will be, or 5-fold cross validation will be good enough. If you have, you know, 100 points, you know, having too many folds might be a little bit difficult. What is the difference between test set and external validation / test set? I'm not sure what does it mean, external validation. Okay, other validation data go from the shuffling the original data as well, like. Okay, so this is important point. This other validation data gotten from the shuffling the original data as well, like a test data. Okay, yes. Okay, but what is important here is you take your first split and you split everything into the training and validation and test. And test you don't touch. And now you take training and you take this chunk, which is training and validation, and slice it as you fit. But you don't touch the test data. You never touch the test data, because in the moment when you touch the test data and perform some testing, you are getting information about performance of your model. And if you fit it back into the model, you are kind of partially training of your model on the something which is untested, which you're not supposed to do. Because this you do kind of ideally, the last bit you do only for the answer. So you have done all your training on training and validation chunks, but test, okay, so you're ready for your answer. You calculated all folds. You done all your tests. From here you can calculate what is your mean performance, what is your mean precision, whatever is your kind of metric of success. And for example, MSE, you can calculate the variance of MSE. Not MSE, sorry. You can calculate the, yes, yeah, you can calculate the MSE, but afterwards you can calculate the variance of MSE, because what you want to know that the mean square error, how it's differ, for example, for each of them. And kind of if the variance of that is low enough, you can claim that, okay, it's probably whatever you train is sitting in the values of the model, or kind of in the parameters of the model, not in your data. How you determine the optimal k value from cross-validation? You just choose the k value. And as I told you, typically it's 5 or 10 if your data allows that. In here, in this example, it's 3, but I assume it's just too small data set. Okay, so now the second strategy, which is much better, which does not involve inverting of the matrices, and is doesn't based on existence of the analytical solution. And that is why it could be applied to any models. And this is called gradient descent. And the gradient descent is based on the following on the very following idea, simple idea. So you choose randomly some set of betas, and that is parameter which you can choose, how you choose your initial values of betas. So you can choose them from the Gaussian distribution, you can choose them all be equal to 1, you can choose them all to be equal to 0, which might be not a good choice, or there are different strategies. So now afterwards, what you do, you calculate the gradient of your loss function at this value of beta, and now what you do, you update the value of beta. And this is beta is not one number, kind of like it's kind of the set of numbers. You update it with the gradient, so you go in the opposite direction, because what the gradient is doing in mathematics, it's a vector which is pointing in direction of the growth of the function, but you want to go to the minimum, so you need to go to the opposite direction, and you choose the step how quickly you go, and this is called learning rate, and that you can also it's also required optimization. Because you can take it very small, and in that case, you train for a very long time. You can take it very large, and in that case, you can jump over your minima, or you can, but you need to choose it right enough. And very typical strategies in many algorithms are kind of in the serious algorithms that you start small for some time, but afterwards you slowly increase it. Okay. Okay, so how it works? Yes, we have some landscape of our loss function from the function of betas, and essentially, yes, what you need to do, you need to walk to the minima. Yeah, and the gradient in this point will be pointing upwards, so that's why minus gradient will be pointing downwards. Okay, so and now the problem is that when you choose the gradient, you can be just by whatever reason walk into the not into this valley but in that valley, and that kind of you can walk into the local minima, and the gradient in this local minima will be kind of small enough so that you will get stuck in this local minima. And what it depends on, it depends on where you start walking from, and that is the choice of the initial. I mean, one of the reasons is the choice of the initial values of beta, and of course the initial also the value of learning rate alpha is how far you jump. Okay, so with the gradient descent for the linear regression, everything is good because it's so-called convex. So it's mean that it's look like this ball, but in many dimensions. If you have a multi-dimensional problem, it's mean that there is no local minima, there is only global minima, and if you walk along in opposite direction to the gradient, you will hit it. Okay, so that's a little bit more on that, but essentially logic is the same. But again, luckily for us, it's all well enough implemented, and the gradient descent is not the only method. There are several other methods how you can make it more efficiently. For example, one of the problem is with the gradient descent calculation, if you have a lot of very multi-dimensional data, you have a lot of components in your gradient. And if every time you need to calculate a derivative of it, it's going to be very time-consuming. And so what sometimes is done, you randomly choose smaller section of the directions on which you want to calculate the derivatives, and you kind of estimate the vector of gradient, and you go in that direction. On the next step, you again resample, choose some smaller set of the vectors along which you want to go, and by doing that, if you do things good enough, and if you're lucky, you end up in the proper minimum. Okay, so there is to the question, yes, that I came across the splitting strategy a lot on the internet: training set, test set, and external set. Okay, yeah, you can use it, but in this case, you train and do it on the test set. You don't touch the external set. It's just a different nomenclature. Okay, yes, and how often we do the gradient descent until we reach minima, so it means that we find the convergence. Okay, and convergence means the convergence in the loss function, so that the loss function do not change in anymore. Okay, yes, kind of repeat until, yes, so kind of you're changing the betas, evaluated with respect to some norm because it's a vector, so it's smaller than some given epsilon, which you can also choose, which is, yes, small enough. Okay, so learning rate. So if your learning rate is too small, you will just move very, very slow around the slope, and you might be moving in the right direction, but it takes too long. If your learning rate is too high, you might jump, and this could be such that you even jump in the wrong direction. So from this point of view, yes, you want to really choose the learning rate carefully. And as I mentioned to you, the typical strategies are, people use kind of the learning rate which change with time. Okay, so next will be the classification, and I think let's see where we are. Is it okay to keep multiple test sets? Okay. It's okay to keep one test set or one subset of data for the final test in which you don't touch. So you take it, you in the beginning, you slice it off, you put it away, and you don't touch it. So this is the right way of doing it. And with remaining data, you can slice it using the validation or whatever. Kind of you can slice it again, and then some part you train, some part you test, and you don't mix it. Okay. Okay, so I think let's go to we still have a little bit of time. Let's not start the classification, because the classification will be the short bit. Let's speak about classification a little bit later, and let's go into the tutorial. Let me reshare my screen. Okay, so you should be able to see my screen. And let's start talking about a very simple problem of the linear regression. Okay. And there should be a file in the okay, so what you need to do, so kind of in the canvas there is a IPython notebook as well as this file with the data. Yes, so kind of what we will need a NumPy for the clear things, yes, pandas because we are going to work with the data set, matplotlib because we are going to plot a couple of pictures, and Seaborn is also for plotting. And essentially, we need a scikit-learn, but we'll just look at it just now. Okay, so we're loading data set and looking what do we have. So, and this is essentially a data set which is having the whole bunch of very famous data sets or standard data sets, and one of those is this housing prices data set, and at least one version of it, and it's kind of average area income, kind of like there is an address of the house, there is a price of the house, but there are extra things which determine or kind of seems to be reasonable. Yes, average income in the area, average age of the house, average number of rooms, and average area of kind of in the area, kind of how many rooms on average in this area in the houses, and how many bedroom on average is in the houses is in this area. Okay, and there is a kind of some given address and there is a given price. And of course, the task is to train the model in such a way so that we can predict the price, and we're going to do it with the simplest and dumbest possible model. We're going to do it with linear regression. Yeah. Okay, so you all have Python, so you all can run it. Yeah. So let's go through the code and try to understand what's going on. So I assume these comments you've seen, yes, in your pandas part. So we could also give a look onto data frame info. So we have 5,000 entries, yes, and they are all full, they are all non-null. It means that we don't have the problem which was mentioned already in the question. We don't have a problem of data cleaning. So it means that we have a data, because the problem of data cleaning is a separate and serious issue, which, kind of like in the real life one needs to deal with. And there are several strategies. Okay, so we can also look on a little bit of statistical characteristic to see what are the percentile of the distribution of the numbers in our data. Or we can do it in a graphical way. So we can look on the columns, and we can now ask that Seaborn to do the kind of pair plot for us. And what does it will do? Just now, it's going to plot us, for example, on the one axis, average area income, and price. And from this image already, without big knowledge of machine learning, we could see that, okay, the higher the average income in the area where you want to sell your house, the higher will be the price, at least in that in the data set of this US data. But the, for example, area population or average age of the house is almost all over the place. Yeah. So and already based on this kind of very simple plots, which you can do from the seaborn, you can already have a little idea of what's going on. Is everybody doing okay with IPython notebook? Okay. Okay, good. So, or if we want, we could plot particular given, you know, particular given column, what the distribution is, and we could see that the distribution is looking very nicely and almost Gaussian, and like where the majority is kind of is in the center, and we have our little tail. So there is not many in this data set too cheap houses, and there is not many overly expensive houses with respect to this data set. Or we can do the, I don't know, we can plot the density of the prices. Okay, another thing which is also interesting is to try to give a look, because I mean, already from here we could see that, you know, there is a correlation between the price, average area income, and the price. And in statistics, you can evaluate the correlations of corresponding input points, and that is very nicely done by pandas by doing DF correlation. And so we have calculated some correlations, or we can very nicely present it using the heat map, which looking like this. So, and we can see, of course, the, you know, average area income and average area income is absolutely correlated with itself, yeah, because it's the same data. But for example, yes, you could see that there is negative or kind of very little correlation, no correlation with average age of the houses in the area, or kind of the little correlation with average number of rooms or average number of bedrooms, but there is again very good correlation between the area income and the price, and so on. So there is a correlation also here between the average number of bedrooms and the average number of rooms, which is kind of understandable, yeah, because the more rooms you have, the more bedrooms you have. Usually that works like that. Usually it's not the case that there is a 1 bedroom and 25 other rooms in the kind of in the normal household. Okay. And so this is a little bit of statistical information. And now we can, what we can try to do now, we can put it to our linear model. Okay. So first we need to kind of to separate information which we need and which we don't need. So let's just get a list of the columns. And we need this data, because this is a data of interest, yes? So kind of this will predict something about price, yes? Average area income, house age, number of rooms, number of beds, and so on. Price is the variable which we want to predict, and address in this case is irrelevant variable, yes? Because address doesn't mean too much, or kind of address could mean something, but usually what one need to do in that case, you need also to add geostationary data, and for example, and see how one address is related to the other address, kind of using some, you know, maps and things like this. And people do work like this, but that's much more advanced for our little linear model. Okay, so our X, or our kind of input data, will be the columns from here to here. Yes, so this is all our input data. Y is this column, and we could check it, yeah, and we could see that, you know, that yes, our input X is looking like this, yes, so all our areas here and our prices are here in the column. Okay, somebody is writing that he have not been able to install JupyterLab, but you don't need a JupyterLab. You can just do the Jupyter Notebook, or if you don't have a JupyterLab or Jupyter Notebook, just use the Google Colab. Just log in into the Google Colab and load. I mean, I assume that you have a Gmail account, so it means that automatically you are a member of the Google Colab. You just need to login, you can upload this IPython notebook into the Google Colab and execute it there. Okay, yeah, Spider also works fine. That's I absolutely agree. Okay, so now we're coming to the test train split, and you see that's what I meant to you is that, you know, scikit-learn, sklearn have this kind of built-in, so you don't need to do it by yourself, and kind of there are some typical parameters. And let's do this. Yes, scikit-learn. How's called it? Just because there are a couple of parameters which are interesting, which you might consider in future. So let's go here. So in particularly this parameter. Yes, so scikit-learn model selection train test split. It's have kind of, you have your input data. So you can choose your random state, and you kind of, if you don't choose your random state, it means that every time you execute the algorithm, it's going to be different random splits. Okay, and shuffle true is a very interesting parameter. It means that, you know, and by default it's true. It means that now your data, before it's going to be split, is going to be reshuffled. Sometimes you want it, sometimes you don't. So just keep it in mind. And test size 0.3 means that the third of the input and output is going to be used for the test, and all the rest is going to be used for the model training. Okay, so, and we can check. Yes, so we can check that training size is 3,500 entries with the 5 columns. Is it correct? 1, 2, 3, 4, 5. Good. Yes, kind of test set will be 1,500 with the 5 columns. That's correct. And the training output, training wise, is 3,500 entries and 1,500 entry. Yeah, good. So we're good to go. So now, what do we need? We need, again, from the scikit-learn, we need to grab our model, and also we'll need the metrics to evaluate the performance. And creating model in scikit-learn is as simple as just writing, okay, this is our model, and model is created. And now we need to fit it. So when all that happening, and we just need to write linear model, fit, training data, X train, Y train, and it's done. Okay, so now we could, because we are dealing with the linear function, we can get interested in some coefficients. For example, you know, what is the intercept term, because we fit in like linear hyperplane in our data. What are the coefficients of the linear model? So, and now kind of, or we can put the coefficients, you know, in a little table, on a little data frame, and print it, so that to know that, okay, for the average kind of array income, we get this coefficient. For the average house age, we get this coefficient, and so on. And essentially, that's all. Kind of, we have trained with you the first linear model. We haven't done yet serious pre-processing or any kind of in general required pre-processing, but this is just a simple, very simple notebook to show you how it works. And we can also plot a little bit of a few more graphs, which are showing us relationship between the between the kind of the features of the trained model. Okay, so, and I mentioned to you that R-squared coefficient, so we can also calculate that, and for that we need that metric module of the scikit-learn, because in the metric we can do it's just R2 score, Y train, Y predicted. Sorry, yes, I didn't mention. Okay, to get the predicted data, yes, from, because that was, we create model, we train model, because we fitted the training data to the outputs. And now how we predict, first we can try to predict the train data, so we can see what is the performance of the model on the training data, and the R-squared coefficient on the training data is looking like this. Okay, and now we can predict test data, which is unseen. Yes, and kind of we do again predictions, linear model predict test data, and what we are going to get. So we get some Okay, so this is first prediction, but I think also, yes, there is a R squared is coming. Okay, so what we can do now, which is very interesting, which can for this kind of models, which is very informative graph, we can plot what is the predicted value of the price or predicted value of the interest vs real value of the interest, because we know it, yes, because we know the Y test. Yes, so we can do a scatter plot between the Y test and predictions. And essentially what you want ideally, you want a straight line, yes, because if every Y is a prediction, it's kind of, you get a test or kind of straight line, but this is also extremely good fit because because of the noise and because of the simple model, it's very good. You know, you don't have the points here, you don't have a points there, you kind of, you are more or less going along the Y is equal to X line. And this is very good. So, and now we can just, yes, calculate all possible functions from the metrics which were there. Yes, kind of, we can calculate that mean absolute errors, mean squared error, root mean squared error, and we can calculate this R2 score. And you see what you are getting, which is fine, and which kind of good sign. So first of all, you get R2 squares, which are R2 scores, which are comparable, but this one is a little bit higher than this one, yeah, which is okay. Which is exactly what you expect, because usually, because when you do it on the, because this is performance of your data set or of your model on the seen data on which you train, on the trained data, and this is performance on the unseen data. And you know, the fact that they're comparable but on unseen data is a little bit smaller is a good indication that, okay, we're going in the right direction. Okay, so okay, so if you have a CSV file on your laptop and you want to run the Google Colab, in the Google Colab, you also need to throw the file into the Google Colab, and the file is minuscule, so it shouldn't be a problem. Okay, and I think in your analysis of choosing most efficient input variables toward the output variables, how did you come to the decision that the address variable is not relevant, as it is not even included in correlation metrics? Because the address variable, first of all, it's not a number. Yes, kind of like, in order to analyze address variable, you can analyze address variable, but you know, very often you get these variables which are not really relevant right now, and you might decide that what you wanted to do with them later. Because what does it mean you need to analyze address? So you need to, I mean, it might be a relevant variable, you know, kind of like in some situations, you know, when this street is a very highly ranking street and neighboring street is not so highly ranking street, in that case, address is important variable. But in order to be able to parse it, you need to be able to take a line of address, separate it to the, you know, road, number, you know, suburb, and afterwards you need to have an X kind of, and in this case, you will need to take an address line, split it into the bits and pieces, like, you know, road, suburb, house number, and afterwards analyze, kind of to do kind of to introduce it as the input variable into your data set and analyze it with some other ways. But and if it's a textual variables, you need to use, I don't know, some text to vector conversions and things like this. So it will be, it's not that it's irrelevant, but I mean, it's irrelevant, kind of, it's outside of scope of doing with this little, you know, linear regression analysis. Because in order to analyze addresses, you need to do much more, and that might be relevant. But as always, you know, there is always a question, you know, how much time do you want to spend in building the good enough model? And for that, you need to know for yourself what is good enough. You need to really to define it, what the good enough means for you as the person who is training model, you know, kind of. So, and that's why, yes, is the way to determine the variable importance, and there's to determine, yes, there is a way to determine variable importance, and we're going to talk about in the kind of a more advanced tutorial, because here we could, so first of all, there are statistical ways of determining the variable importance, but also here the problem is why we cannot just interpret the coefficients in the linear model as the variable importance, because our input values are not normalized. Because the scale of our input values is very different, it's very difficult to say is variable A is more important than variable B, because if the variable A and B are not comparable to itself. But I think in statistics, there is this, it's called the t-statistics. There is an approach, and I think it's a part of the scikit-learn. So you could do it, and afterwards you can take the variable importance, and that is good comment in the sense, like, because when you're dealing with the very large data sets, that's exactly what you want to do. You want to separate what is out of your all possible values, what is important and what is not important, what you can ignore. Do we have to pip install scikit-learn model to import it? Yes. And I think somebody already replied to this question. Yeah, if it's not there, yes, you just try to import scikit-learn, and if it doesn't work, you install it. Okay, what is acceptable gap between training and test accuracy to rule out overfitting? Okay, it depends, you know, and we haven't ruled out in that model overfitting at all. The only kind of, we haven't done in that particular model, we haven't done any analysis to decide, does it overfit or does it underfit? We just seen that, you know, on the trained data and the predicted data, our two scores are comparable and they are good enough, take into account that our two, the perfect is 1, so they're in the 90s, so 0.9, so that's good enough. So that's a good indication. But in order to check, do you overfit or underfit in this case, what you need to do, you need to, because we were playing only with one model. In order to do it kind of more seriously and to talk about, you know, overfitting, underfitting, we need to play with the kind of, we need to increase the capacity of the model, because let's assume that we overfit with this model. The question is what we can reduce, which part of the capacity of the system we can reduce, because it's already a linear model. There is nothing to reduce. So it's only could underfit. This particular model could only underfit or fit good enough, but this could not overfit, because if we would have some extra features which we created, in that case, yes, we could probably play the game of underfitting and overfitting. How do you know there is a correlation? Yes, it's yes. 1 is perfect correlation, 0 no correlation. Yeah, but also just look on the graph. You know, just look on this graph. I think it's explicitly saying that there is a correlation, because as you increase the number of bedrooms, the average or average income, the price is increasing. So you see kind of like they are aligned, and that I think is a. Okay, so when I have a question, what data size is sufficient for doing machine learning? Any data size. It just depends, you know, what kind of machine learning are you doing? Okay, so what else do we have? Given new values, how do you use the model to predict? Okay, but that was right here. So this is predictions is LM test, and what you can do if you what it is, test, yeah. So X test is a data which we haven't seen, and you know, when we do this, or we can just see predictions. That is kind of a new data of the prices. If you want to give completely new data, what you need to do, just invent and create a data set with, I don't know, one entry, invent some average kind of the values here, and here, and do this linear model dot predict x your new data. And what you will get out one number which this linear model is thinking should be the price of that property in this particular case. Okay. So when does it become important to take causal relations into the account? Causal relations between between what? Between the input data. It becomes important because of sometimes it's important, sometimes it's not important. It just means that, but that's what we are going to to talk about when we are going to talk about unsupervised learning and dimensionality reduction. Is that, you know, if you have a two input points, kind of two types of data in your input which are very correlated, you can construct some sort of, you know, a composite input which will be built out of these two input streams, so two columns, which will be one. So, and if your data have, you know, 20,000 features, but, you know, 1,000 of them are correlated or behave roughly the same in a almost perfect correlated way, it means that you can, most of them you can throw away and leave only one, or there are fancier ways how you can do it. And the simplest way of doing that is called principal component analysis. And we're going to talk about that soon. So do you think false correlation can indicate overfitting? Yes, k-force cross validation could indicate overfitting, of course, because what you are getting from k-fold cross validation, you are getting kind of the result of the training loss on the multiple, you know, splitting between the train and validation. And, you know, if all these numbers are high enough and there is not large variance, it means that, you know, it's what you're picking up that your model do not reach a good enough loss without, yes, kind of, and this is consistently irrelevant of the kind of split of the data. So it means that it's really something wrong with your model. How can you optimize the parameters of your model? That is coming after the break. I think, don't we supposed to have a break? Because in this simple kind of tutorial, kind of for this kind of file which we've seen now, we don't do anything seriously. Like, I mean, it's just, you know, a simple out of the box things. But in this example, which will be a little bit more involved, we're going to look into the kind of where it is. Yes, we're going to first of all standardize data and so on and so forth, kind of like that, so that we can talk a little bit better about the feature importance and so on. Okay. Okay. Yes, Adishina.
Thanks, Prof.
Hello, good morning. Thank you so much for the training. But I have a question. I see you haven't spoken concerning feature normalization and standardization. I just want to ask. And my question regarding that is that while doing that, is it about to do the normalization before splitting into training and test sets, or one has to split first before doing that? Which one is much more advisable here? Thank you.
Okay, so this is, in fact, is a very good question, because what you want, at least, you know, my understanding is that you need to do the kind of, you can do both, but the idea is that when it doesn't really seriously matter, if you manage, when you do the splitting, to do it homogeneously. So when the test and training coming from the same, you can make sure that they're coming from the same distribution. If you cannot make sure that, it's better to do normalization before, but to do normalizations which are kind of, because there are different types of normalizations, and there are normalizations which depends on the collective properties of your data set, for example, min max. So when you look at the minimum and maximum value over the whole data set. So, but there are some normalization which is just, you know, bringing to the Gaussian value. So that I think you can do on any stage. But that we'll have just now in this another example. Because yes, we'll first do normalization. Yes, we'll first do normalization. No. Essentially what, okay. So what we will do in this example, we'll first do the split, but we'll apply the same because we will apply. Yes, okay, so what we will do, but you will see it just now, we'll first do the split. Afterwards, we'll train the transformation on the trained data, but apply it to both trained data and the test data.